of this event. For those people watching on demand, welcome to YouTube Civil Engineering Live. During this event, I'm joined by my colleagues. I've got my colleague Matt Fellows here. Matt, can you tell us what you'll be doing during this event?
Hi Dion, thank you very much. I'm going to be demonstrating some of our materials testing equipment.
Fantastic, thanks Matt. And we'll also be joined by Kyle Hatchard. Kyle, you're on structures, I believe.
Yep. So I'll be talking through our structures range. So we've got 19 different structure range that we supply. However, we'll go through 4 of those just to give you a bit of an introduction.
Fantastic. And supporting Matt, let's not forget Kanna. Kanna, come and tell us what you'll be doing.
Hi Dion, I'll be demonstrating the flow channel behind us and testing an ancillary.
Great, right. Well, before we get started, I'm going to level the playing field somewhat. Some people are a little unfamiliar as to what civil engineering is and where it all began. Well, civil engineering is all about the built environment, whether that be the man-made built environment that we're managing, designing, constructing, maintaining, or whether it be the natural environment. And it dates back thousands and thousands of years. We can think back to the ancient Egyptians with the pyramids. But it wasn't actually coined as an industry term until the 17th or 18th century. And over that time, compared to today, there are some common challenges like safety. We've had some recent devastating disasters that remind us how important getting structures are right, understanding materials are. Then we were also, at the same time, we've got new challenges in the world today. We've got issues like climate change, the reduction and loss of biodiversity, and with that also an increase in population. These create new challenges for the civil engineers, whether we're looking at rising sea levels and flood defence systems, whether we're looking at storm damage and exposure to bridges and roads. And with the rising population also means increasing congestions on our roads. We've also, another element is technology. Technology is always helping us, but it's often very much hindering us. And that's very much true for civil engineering as well. We've got the rise of digital cities and all the wonderful things that it enables for society, but also the challenges that come with it too. Here at TecQuipment, we're all about providing the fundamentals of engineering basics. So it's understanding all about things like materials properties, all of those specific things that civil engineers need to start off in their first year or second year of study. And it's those foundations that we want to see helping students so that they're more employable. Recent research found that 62% of employers felt that students weren't ready for the world of work. So we've got some way to go. And this is why we're doing this YouTube Live. We want to help bridge that gap. Sorry for the pun. Now, before we go on to looking at our demonstrations, our equipment, those pieces of teaching equipment available in the market, I'm going to give you a bit of insight into our bridge building competition. This was the surprise that I alluded to during the preview live streaming last week. I can hear them coming into in my earpiece right now. What is happening here, for those who've arrived later on in this live streaming, is that we've got 2 teams of people from across the TecQuipment organisation who are going head-to-head against each other to build the best bridge out of spaghetti and marshmallows. But that's it from me. I'm going to pass it to Adnan Rafai and let him, in the other room, tell us more about this bridge building competition.
Hi Dion, we speared ahead here and started a little earlier, but let me tell you, for those who just joined us now, we have a task in the bridge building room for building a bridge. We have 2 teams, each team has a set of spaghettis and marshmallows. They'll have to build a strong enough bridge that spans a predefined area. Not only that, it'll also have to hold specific weight. The bridge that will withhold a strong mass or a heavier mass than the other will be the winning bridge, and therefore the team will be the winning team. We've got 2 teams. We've got Team A or Team B over here, and let me introduce you to this lovely bunch here. We've got Sarah.
Hi, I'm Sarah from Finance.
And
good afternoon, I'm Nick, I work in purchasing.
That was Nick, and last but not least we have...
It's Marcus, I work in planning.
Thank you, Marcus. On the other side, we have Team A, led by...
Robertson Test.
Antonio from Sales.
And Phil from sales.
Now, no game will be complete without somebody judging it. We've got our own judge. This is Andrew Ratcliffe for you guys. And Andrew, can you tell us how do you see this going in the next hour?
Well, both teams have made a good start. Let's see what happens over the next half an hour or so. We'll come back with some updates, but we've got some promising designs in the offing already.
Dion, I think we're having a very exciting hour to look ahead to here. Over to you.
Wow, that does look exciting. It's a very good foundation starting there. Right, what I would like to remind you, if you're watching live, you can post suggestions to our bridge building teams. They might not be as good as you are, so please do put them in the comments box. Put your other questions in there as well so that we can ask those to our specialists. Now, I'm joined back here with Matt Fellows, and Matt's going to be telling us more about our materials testing range. Matt, over to you, and a fatigue tester, I believe.
That's right. Thank you very much, Dion. So as Dion's just said, I'm going to start talking through some of our materials testing equipment. I have a few pieces of materials testing equipment here. We have some tensile testers and a fatigue tester. Now, from the perspective of civil engineering, obviously understanding materials properties is quite a large foundation that students need to understand early on so that they can correctly design their structures with the correct materials. So to help with that foundation, on my left here we have the fatigue tester. So our fatigue tester is driven by a motor at the back here. The speed of the motor is then picked up by an inductive pickup here. The inductive pickup reading is taken by the electrical control box, and it then gives the rate of rotation in hertz and the count, the number of cycles since the experiment started. Over here in this clear plastic guard, you can see that we have a specimen set up. The specimen is quick and easy to remove. It fits into a gimbal ring on one end, and on the other end it is held into a chuck. With the gimbal assembly, that is connected via a load cell and a connecting arm to a moment arm, which allows you to load up the specimen. As the specimen is loaded, as the mass is moved, the specimen load changes. So this allows students to test different materials and to look at the effects of less force acting on the material. The guard itself is interlocked. This prevents students from being able to start the experiment without fitting the guard, which is an essential for safety feature. When the experiment stops, we also want the count to stop so that we're able to take the data that we need. The way that we have done this is with an actuator arm. The actuator arm acts upon a micro switch that cuts off the power to the motor, and consequently we will stop counting. On the left-hand side here, you can see the electrical control box. The electrical control unit is very, very simple to use. It's extremely intuitive, and this is a big thing for us. We want our products to be intuitive because we want students to spend their time learning the principles rather than learning how to use a complex piece of machinery. There's a simple start-stop here for the motor, and you can control the motor speed using the pot over here. An emergency stop allows you to very rapidly stop the equipment in the case of an emergency, and a press to hold 0 for the load reading. The load, and as I said before, the rate and count are given on the screen here. I'm going to pass you back to Dion now.
I've got a quick question here from somebody. The question is, can I use my own specimens?
Yes, so that's correct. So when you receive a piece of our equipment, we also provide you with a comprehensive manual. And in the SM 1090 manual, you'll find an engineering drawing of the specimen. This will allow you to make specimens out of whatever material you would like and test them within the fatigue tester.
Great, you got the product name right. Fantastic. And now this is the point where we want to see what the bridge builders are doing. What's the progress like there, Adnan?
Hello and welcome back. I am here with Team A, which I have been watching over the last few minutes, and I have to say they destroyed lots of spaghettis, but I think that we've got some progress. There's some shape. What will that shape look like at the end? I don't know. Are you confident? You think you've got a good start there?
We're sort of working on it. We're not quite there yet. We're still in a sort of a bit of a prototype stage, very much so, but we're working on it, and we're confident we'll get there eventually.
Spoken like a real engineer. He's got a prototype and he's working on it. Andy, what do you think?
I've looked at both teams' efforts, and I think at the moment Team B are slightly ahead. But there's a long way to go.
We'll come back to Team B in a little while, but as you can see, Dion, we've got some progress here, so I'll send it over back to you.
Great, good stuff. Great to hear that. Right, okay, I'm now with Matt, and Matt's going to be looking at tensile testing, aren't you? Yeah, Matt, are you? Yeah, I think you are.
That's correct, Ian. There's a few more aspects that we're going to look at as well, but yeah, we have 3 units here that are all capable of tensile testing. The first unit that we have here is from our engineering science kit. Our engineering science kit allows students in the early years of their engineering journey to begin looking at the principles of both physics and engineering. In this case, it is a very simple mechanism that just measures the load on a deflection indicator here, and also you can measure the deflection of the specimen using a sliding scale on the right. Next to that, we have the SM1002, which is our 20 kilonewton benchtop tensile tester. The 20 kilonewton benchtop tensile tester, again, is very simple in its construction. It has a load cell, a calibrated load cell that's picked up and read by the digital load meter here in front of the equipment. At the back, we have a vernier that acts as a elongation indicator. The load is applied using a fine hand wheel here, and at the back of that we also have a coarse hand wheel. The coarse hand wheel allows you to very quickly and easily set the distance in the experimental area here. You can engage and disengage this simply by removing a pin. As with a lot of our equipment, this is compatible with our versatile data acquisition software. The data acquisition software will pick up both the load from the load meter and the deflection from the deflection indicator. Now, what's really great about the SM1002 is the fact that it allows students to really engage with what's happening within the specimen, because they're using a mechanical method to load up the specimen. They get a great amount of engineering empathy from this unit. In front, you can see an optional extensometer. When we're working within the elastic region of the deformation, we really need to be able to pick up a very accurate and very small elongation on the specimen, and that's what we use this extensometer for. It connects directly to the specimen, which means that it's only picking up elongation occurring within the specimen, and it's not picking up any effects from the mechanism itself. This allows students to look at the Young's modulus and get accurate results from that. Moving on again, we have our 100 kilonewton universal test machine. The 100 kilonewton universal test machine, unlike the SM1002, is loaded hydraulically. Because you are manually loading this, again, you're really able to engage with what's going on in the experimental area. This is something that you're not necessarily going to get from industrial style machines. The load is applied using a hydraulic ram, which is pumped from the pump here. On these 2 upright struts, we have strain gauges. Those strain gauges allow us to look at the at the elongation within the strut, which in turn is then turned into the load on the digital load meter down here. In the same way as the SM1002, you can get an optional extensometer for this, which again allows you to look at that elongation within the elastic region and calculate your Young's modulus. Both the SM1002 and the SM1000 are provided with, or can have, optional ancillaries. So the SM1002 optional ancillaries will allow you to add a compression cage and Brunel hardness testing. The SM1000 has both of those abilities. Compression takes place at the top here, and you can fit a Brunel hardness testing kit. However, you can also carry out cupping, double shear experiments, disc springs, coil springs, and various other materials testing experiments. I believe Dion's trying to come in here, so I'll stop talking.
Thank you, Matt. You need to carry on talking. I've got some questions for you. Right, the first question is, can I test concrete?
Yeah, that's a good question. So as I pointed out before, we have this compression area here. Within that compression area, you can test concrete. Due to the way that we build the SM1000, the loading of that for your compression test will be exactly the same as your loading for your tensile test.
Fantastic, you're not done yet. What is the cross-sectional area of the specimen?
Okay, the cross-sectional area of these specimens is around about 9.75 millimeters. Again, as I said with the SM1090, we provide the engineering drawing to allow you to also manufacture specimens of different materials if you would like to test those.
Okay, just a couple more questions. Sorry to bombard you, Matt, but what specimens come with the equipment?
So we provide 3 steel specimens. We have 2 at 0.2% carbon off the top of my head, and 2 of them are normalized, 1 is as drawn.
Right, you're nearly done. For this bit anyway, is the load automatic? How does it work?
Okay, the load is not automatic. As I said, we manually pump up the RAM, and this allows students to engage with the experiment. It allows them to, it keeps them engaged as the specimen begins to neck and yield, and as you go through the ultimate tensile strength.
Fantastic. As we saw last night with our Friends and Family event, where we had various staff members, friends and family come along and join us at the factory, where we demonstrated lots of pieces of equipment and even let the kids get hold of and have a go at using the universal testing machine. It really did go down very, very well. Now, Adnan, we're back to your bridge building progress. Are you on Team A, I think? Over to you.
Dion, I'm on Team B. Stay with us. I'm on Team B. And we have fantastic progress on Team B. You would not believe it. I am not sure whether you can see what has been achieved yet here, but we have an excellent looking bridge. This is a team with no engineer, by the way. So with no further ado, Andy, how do you think this is going?
I'm very impressed by Team B at the moment. Yeah, I can see good progress, and I can tell that Sarah is a Cub Scout leader. She's used to challenges like this, and yeah, they're doing very well.
Well, the inspiration here, Nick, can you tell me, was this a Sydney Harbour Bridge inspiration? Was it a Golden Gate Bridge inspiration? What were you aiming for there?
If you're going to aspire to any bridge, Adnan, it needs to be the Humber in the greatest county in the world, my friend.
Oh, said like a true gentleman, said like a true gentleman. Thanks, Nick. Dion, I go back to you.
Brilliant. I like that, Nick. Very, very good. Before we get on with it, I want to do a quick shout out to Hannu Kalavianian in Finland. I'm sorry if I've pronounced your name wrong. The next thing is we're going to be looking at fluid mechanics. It affects lots of areas of civil engineering, and with climate change issues, then it's likely to affect us more. I have with me Kanna. Kanna, I'm going to hand over to you to tell us more about what we have here.
Thank you. For those of you that missed the start, my name's Kanna. I put the Kanna in mechanical engineer here at TecQuipment. And here we have the FC50. We also do the FC80 and the FC300. The numbers represent the width of the flow channel. This FC50 has 12 mil acrylic sides and an aluminium bed, which is connected to the hydraulic bench you can see here. I'll turn this on for you right now. So the flow rate is controlled with this gate valve here. And different students can put in different ancillaries, which you can see here. We have the Venturi sides, broad crested weir, sharp crested weir, crump weir, a drum gate, sluice gate. But I'm going to ask my friend here, Matt, to help me. Matt, do you want to be my civil servant?
Before we hand over to Matt to be a civil servant, I want to let you know that we have a poll. You have the opportunity to vote which of these teams is going to win the bridge building competition, which is going to create the strongest bridge. So if you look in the comment box now, click on that poll, start voting. You can continue to vote throughout our live streaming. Sorry, Matt, I'll pass it over to you now.
Thank you very much. I believe Kanna's got a little bit more talking to do yet.
So Matt, do you want to pick an ancillary, any ancillary, and load it into the Flume? Oh, Matt picked the Venturi sides. Good pick, Matt. So the Venturi sides are made of 3 components. It's an expansion, a throat, and a contraction. As you can see, he fits it. The back side is an aluminium side, and this is an acrylic to see the depth. We also have a depth gauge here to measure the upstream depth. And Matt's going to close the sluice gate now. And as he does this, an hydraulic jump will form. So as you can see, the hydraulic jump is moving towards the Venturi sides. It's quite a slow process. Got to go with the flow, really. And another question.
I've got a question. Okay, while you're waiting for that to catch up, can you use this channel for sediment transportation?
The FC50 doesn't have sedimentation, but the FC80 does, and the FC300 has a sediment loop included. Do you guys got another question?
You've answered the question about do you have any self-contained closed loop channels?
That's for Matt.
Oh, okay, wonderful. Yeah, so as Kanna's just mentioned with the sediment loop, like he says, we've got sedimentation on the FC80, and there's an optional extra as well on the FC300. You can buy that sediment loop, which recirculates the sediment. Both of those channels, the FC80 and the FC300, are self-contained flow channels. So, in other words, they have reservoir tanks that come with them. The FC50, being a starter hydraulics lab flow channel, is part of our modular fluid range. So it's not self-contained, but it is easily powered by the H1F, which can then be quickly disconnected in order to power different units instead. We have a wide range of hydraulics equipment for that. As Kanna's just pointed out, we're measuring the upstream head here, and as we close the sluice gate, because we haven't quite got there yet, so as we close the sluice gate, we can watch as this hydraulic jump starts to make its way towards the Venturi flume. And a great experiment for the students is to see that the hydraulic jump, or more to the point, the downstream flow and head makes no difference to the upstream until it crosses the throat. Right, I'm going to pass you back to Dion now, unless we have any more questions.
Yes, Matt, we do have one more question. And the question is this the standard size flow channel for a lab?
Okay, so we actually had this question yesterday as well. Like I explained, the FC50, this is your entry-level flow channel. Now, with an entry-level flow channel, you're always going to get more effect from the boundary layers due to the width of the flow channel. So if you're looking for something for perhaps your first year students or those that are looking at open channel flow, but perhaps it not being a major component of your course, then the FC50 is excellent for that. If you want to expand on that, you want to go to more real world situations, then you're looking more towards our FC80, our FC300, or our currently in development FC600, which is going to have a 600mm working section.
That will be pretty epic. Right, okay, now I want to see how those bridge builders are doing. The poll is telling us that everybody believes that Team B is going to be the winner. What's happening, Team A?
Well, you heard right, Dion, there. We've got, well, I would call it a little of a mess here over Team A. And in fact, let me just read some comments we've had over the YouTube live. Guys, are you listening to this? We've got this from James. Tell Team A they should use uncooked spaghetti. I think this refers to the shape of your bridge. We also have a comment here from Ryan, and this is much more constructive, and it goes, start with the base foundation, guys. Try and do that. Now, yes, I'm not sure whether you can see this
Adnan,
progress.
I've got a quick question for you.
Go
Ryan
for it.
also has a bit of a cheeky other question.
Yeah?
He's asking you this style-based question. Where did you get your shirt from?
Now, my shirt has been made specifically for me. There is a style and a reputation I have to keep, Dion, and you know all about that. I'm sure you do. Now, let's get back to this bridge. Now, can you guys see it? I hope you can, because I think we're gonna have to. We might end up with a comedy act over here in Team A. What do you think, Andy?
Yes. It's the progress since the last time we looked, so they're getting there, perhaps albeit a little bit slowly. I have my doubts about this one.
I have more than doubts, Dion, about Team A. So here you go. I'll send it back to you. You've got a lovely dress, Dion, by the way.
Thank you very much. Right, now with the other style master, we are with Kyle. Kyle's going to tell us more about structures, because structures is one of those things you initially think of when you think about civil engineering. So Kyle, over to you.
Thank you, Dion. So we're just going to run through our structures range. A few points to note before we go into the actual product detail is the fact that everything comes with a 5-year warranty. All products are supported with the product manuals, and they're a great guide to product theory and theory of structures. So we're looking at here in particular the buckling of struts, or buckling of columns as it's probably best referred to, where you can see students are loading a member frame with a force acted on from the top. There's a series of different points that they can actually create, so fixed and pinned, and a pinned configuration to allow them to understand the complexities of the Euler theory. So you can see as well you've got a set of different lengths there, which allows students to then build on that theory and analyse the results dependent on the column height. So something that you perhaps relate to this in real life would be the building of a column for a structure, to hold a building, for example. Or if you wanted to understand the failure rate of a column, something in a steering rack for a car, for example, you'd want that steering rack to fail on the point of impact. So that's our Euler buckling of column pieces of equipment. Just a question from Dion. Go on.
Kyle, the question is, can you use different shaped specimens to what you have here?
Absolutely, that's a great question. So we can do, however, not particularly with this piece of equipment. We have the SM1005, which is a benchtop version, which allows students to then use a variety of different materials on that particular piece of equipment.
And one more question, does this have data acquisition?
Absolutely. So again, mentioning our structures software, that allows you to extract data from a data acquisition point of view and then analyze that. So that also adds a different dimension to the lecture. So you can analyze data from a software program point of view as well as the practical application. Okay, so we're going to move on to the torsion of circular sections. This is a very straightforward piece of kit which comes with 3 specimens. So you've got a solid brass bar and a hollow tube bar as well, and also a stainless bar, as you can see here. Students simply load the specimen through the chuck and then tighten the chuck and therefore apply a load here and you can see the angular displacement along with the polar moment of inertia, which is the calculation the students are able to then understand, taking force readings from the force meter here. So a really simple piece of equipment to understand torsion. Thank you, Dion.
Right, that's it from Kyle for the moment. We'll be coming back to him in a couple of minutes. We're going back to the bridge builders. I really hope Team A is pulling it out of the bag for this.
Dion, it is Team B. It is Team B we are with here now, and I think you can see what they've achieved so far. And look at that. Not only the marshmallows look great, but I think the bridge itself looks fantastic. Well, look, no tips needed for this team, but otherwise they will be finished in a few moments. Andy, what do you think?
I'm very impressed by Team B. Let's hope it's as strong as it looks.
Well, did you get that?
And I've not seen anybody eating any marshmallows yet.
Nick, did you practice for this before you came here today?
I'm winging this as we speak.
Are you really? I've got my doubts. Look, Dion, we've got fantastic progress here with Team B. It's impressive. I'm just fearful for Team A.
Oh,
back to you.
Team B is just too cool for school. Well, come on, Team A, you really do need to get your finger out, get it sorted. We are rooting for you in this room. Now, I'm back here with Kyle. Kyle is going to be talking about roof trusses.
Thank you, Dion. So we're going to quickly go through our STR8, which is the roof truss arrangement. As you can see, you've got a series of member strains here that are set up strain gauges, which then feed into a strain gauge meter, which is calibrated to the individual struts and allows students to understand how these struts in particular react in regards to forces that are applied. We have a force meter here, so you can apply a load, and you can take the reading from the force reading here. Or alternatively, you could apply a force, for example, on a roof, loading of snow perhaps. Or maybe you've got a water tank in a loft, so you want to load and see how those member strains are perhaps affected by that load. So in real life, you wouldn't necessarily see these pin-jointed, free-moving types. You would actually have them as fixed, so they'd be typically welded, and there's a correction factor for that. However, that's not really important when we're looking at this particular piece of equipment. It's all about demonstrating the fundamentals of the engineering principle to the students. So something like Bose notation, for example. So yeah, that's pretty much really the STR8 from TecQuipment. A really good introduction into different structures. And also you're able to look at Warren girders, for example, with the same struts, so you can set that up yourself, and also cantilevers. Over to Dion, I think.
I've got questions for you, Kyle. It's not over yet. Can we load the structure at different points?
Absolutely, great question. So, as we mentioned before, if you wanted to simulate perhaps snow loading on a roof, you could load from an angle here, or maybe even load from the top, and obviously adjust the loading force here, to, like we said, simulating a water tank in a loft, for example. Where you may see a framework like this in real life would perhaps be an electricity pylon. And yes, you know, have a look, see what's out there. All right, thank you.
Now, Kyle, a question I know the answer, but I want you to tell it to me that someone's just asked. Is the truss the only structure you can make? Because I don't believe it is it?
That's correct. So we mentioned briefly before that you can look at cantilevers with this piece of equipment, and also the Warren girder.
Okay, good. Right. I believe the question now is, do you get theory with equipment? We do, don't we? Tell us about that.
That's great. So yeah, everything comes with the lecture guide notes, or alternatively, the student guide notes as well. What does this mean? This means that it talks you through the piece of equipment. So integrating this into your lesson plan is really simple and straightforward. So yeah, no, that's a really good question.
Lovely. Right, what we're going to do now is we're going to go and do one last look at one of the teams before we go to judging. Let's see how we're getting on there.
Dion, needless to say, Team A has got a lot of work to do, but they have got something at least. Phil, what have you got there?
It's a bridge.
What kind of bridge do you have?
It's a bridge that goes up like that.
Antonio, where did the inspiration come from for this bridge?
Dreams of Salvador Dali.
I think it can only be described as that. Andy, Where do you think we're going here?
I think their inspirations come from the nursery rhyme, London Bridge is falling down.
And I think that that's more likely to be the case than anything else. Dion, as far as bridge goes, I don't think we've got a bridge here, but we've got a lot to look forward to in Team B.
Let's see what Team A can turn around in about 1 minute. The suspense is not so huge. I'm going to pass back over to Kyle now, who's going to be talking about suspensions bridge. This is the last experiment we're going to be looking at today, but we'll be looking at judging very soon. Thanks, Kyle.
Cheers, Dion. Okay, so just to summarise then, really, this is our final piece of equipment that we're going to be looking at. Again, just to sort of reiterate that there are 19 different structures that are available to demonstrate different principles within civil engineering. So we're looking at here the simple suspension bridge. This is to allow students to understand how the members react when they load a series of forces, replicating the behaviour of a suspension bridge. What you've got here is some cable, which is then loaded via some weights, and therefore then takes a force meter reading, which is then replicated here for the students to then plot, dependent on where the loads are placed and also the amount of weight. So yeah, a very straightforward piece of equipment that really allows students to a bit of an introduction into a suspension bridge and its behaviour. Where you'd perhaps see something like this in real life would be maybe between two palm trees on a beach, for example, and you've got a hammock and you're loading the hammock with a force, and you can see and understand the deflection and the movement between those 2 points. Also to mention as well that perhaps you could open up a bit more of a discussion with the students around maybe the cable size that you want to use and how cost effective that is, and also the height of the columns and building that into a real life scenario. So yeah, that's pretty much it from me on the civil engineering side. So back over to you, Dion.
Great job, Kyle. Right now, it's time to go back to the bridge builders. The time is now. Let's see the judging. Over to you, Adnan.
Dion, we're in the middle of a civil engineering task here and a challenge trying to get Team A's bridge on the testing platform so that we can see if it will sustain the load or not. We have not been able to move Team A bridge. It's not moving at all. So bear with us a few minutes as we go through this challenging task. It seems that we have had that we've got progress here. We've got progress here. Boom. Now, I think we've got to a point where we can load something, but the bridge is falling down. So in essence, it is easy to disqualify. I think we're gonna have to draw clause on what's happening with your bridge, guys. Team A. Yes, you are. Can we just move it away now and see what we can do with Team B? Can you just pick it up? Thank you. Team B, would you please bring your fantastic looking bridge over here? Go on. Andy, have we got the distance right here for the span?
Right, 35 centimetres.
Oh my goodness. I hope you've got this on camera. Nick, if you could just move towards me here.
Right, so.
I hope you've got this on camera. This is what we've achieved in Team B. Dare I say, looks yummy. But before we go anywhere, Andy, would you tell us how far can we go with this bridge before we...
Team B's bridge has won already because it supports its own weight, which is advantageous. So they're a clear winner, but let's add some weight to it anyway.
Right. We're going to...
With the polls, a second. Do you want to know what's happening with the polls? What the people's vote is?
I would love to.
Well, it's no surprise, really. It isn't a total wipeout. There's an 80% believe that Team B will win, and 20% had faith. I'm sorry to you, 20%. We can see that they've been disqualified. They really need to get in some more practice. But let's see how much weight that bridge really can take.
Look, I've got few words for the 20% who had faith. They were not in the bridge building room. If they were, they would have seen that there was no chance for Team A to go anywhere with their bridge. Now, Andy is loading the bridge. How far have we got so far there? What's the mass?
60 grams.
60 grams so far, and the bridge is standing. And we go into 80. We're going to 70 grams, and the bridge is still standing. We've got a very solid foundation there for this bridge. 80 so far. Team B, it's very impressive, and I can see on their faces they're looking forward to see how far their bridge is gonna go. 90 grams still standing. Are we gonna go over the 100? Yes, we are going over the 100. Shall we keep it at done and leave that bridge standing? We can take some pictures later for a good standing before it collapses. We've gone over the 100 grams mass over here, Dion, for
Brilliant.
bridge B. This is more than what we expected. I think Team A are going to have to go to the revision room and get some... they're coming to you, in fact. I hear they want to come to you to learn a little bit more about structures.
Come over
So
to the
I will
roof
send
trusses.
them-
We'll tell
I
you
will send them
more.
to the roof truss room.
Yes, absolutely.
Dion, over to you.
Right, I'm going to wrap up now. Thank you so much for joining us today for this live stream of YouTube Civil Engineering Live. As I mentioned earlier, if you want to see more live streams from us, we have the on-demand version of Aerodynamics Live. We've got more coming up in 2020. If you do want to keep up to date with all of our videos, please do go on YouTube. You're already on there, but make sure that you subscribe and then you click the notification bell. Then you'll get pop-ups of when we do release our new videos. So that's all from me and the team at TecQuipment, but we do like to go out with a bit of a bang. Matt, you're actually going to start use this piece of equipment for us.
That's right, Dion.
Shall I come around this side so we can all see? So this is Matt now currently demonstrating the universal testing machine. Personally, it makes me a little bit nervous. I get a bit jumpy. Matt, do you want to explain what's happening here?
That's right. So we've just started loading this up. Well, actually, I tell a little lie. I loaded it up a little bit beforehand. And you can see, or we might not be able to see, but there is some very clear necking going on right here, which means we're close to the breaking point. And there it goes. Thank you very much.
Can't help that. Thank you very much for joining us for Civil Engineering Live. We look forward to seeing you next time.